Okay, before we start with the actual talk, I like to make my usual quick announcement. Most of you will have seen me already last time or in one of the previous years. My name is Gertjan Franken. I work for this fine company called G-Data. Actually, I'm in a branch called G-Data Advanced Analytics, and yeah, G-Data does antivirus software traditionally, more than 30 years of experience now, and G-Data Advanced Analytics is more dedicated to IT security related services. So we do a lot of different stuff, and I don't want to bore you to death with all the details right now. But maybe interesting for you is that we are hiring. We offer internships, thesis works, student assistant jobs, and at least the parts, I know the company internships in the next months, most of the open positions are already gone, so we found people for that. Thesis works always depends when you want to do it, but I myself have a small team and I'm currently looking for software developers, so if you're interested in secure software development, stuff like that, and are close to your master thesis maybe or bachelor thesis and are looking for an option, we can talk later. And we also have a project planned where we plan to create some new student assistant jobs. So if you are looking for part-time jobs, maybe we can offer some interesting stuff as well. Yeah, that's from this side. What am I doing here is just inviting you. We are supporting this course since many years, and supporting means we are offering a nice additional evening event. The ones of you who visited us last time will know it already. It's a cozy dinner, a nice atmosphere, good food, good drinks, and a really good place if you want to talk later a little bit to our speaker about details of his talk, or if you want to have nice discussions with technical people from the antivirus environment and industry. It's a good place, I really can recommend it, and yeah, if you have any questions about it, don't hesitate to come to me after the talk. I'm happy to explain more in detail everything. But for now, this should be my part, and I like all of you to give our speaker of today a warm welcome.
Okay, thank you. I'll just switch the presentation for a second. Okay. Okay, so first of all, my apologies for the delay. It's apparently a bad day to use a train today. Okay. So today I'm going to talk about our paper in which we describe how we actually managed to do a comprehensive evaluation of third-party cookie policies in browsers and extensions. And I want to give you a little teaser. Okay, so we tested 7 different browsers and 46 ad blocking and privacy extensions. Now, of those browsers, we found in almost all of them a bug for the implementation of third-party cookie policies, and also for all extensions. So I'll come back to that in more detail. First, a little overview. So first, I'm going to explain some web fundamentals so that we're on the same page about things. Then I'm going to build upon that, talk about cross-site attacks and tracking, how they are performed, what actually the objective is. Then I'm going to talk about third-party cookie policies, how they can be used to protect against cross-site attacks and tracking. Next, I'll talk about the comprehensive evaluation, how we actually did this, and we'll also discuss the results. And of course, in the end, I'll end the presentation with a short conclusion. Okay, so let's start with the web fundamentals. So on the web, when you want to include a certain resource on your own domain that's hosted on another domain. So for example, we have a domain a.com, and we want to include an image that's hosted on domain b.com. Now, we can just do so by referring to this image using the image HTML tag. And then when a user visits this website, first, of course, the browser will send a request to fetch the index page. And using the response, the browser will actually render this index page. Now, the browser will notice the reference to the image that's hosted on domain B, and for this, he will send a separate request. Now, this is done for all resources to which is referenced on the original page. Now, this latter request is also called a cross-site request because it is initiated on one domain and directed at another. Okay, let's talk about cookies. I think we all know what HTTP cookies are. So these are small amounts of data that can be stored by a website on the user's browser. And from then on, they are implicitly included in almost all requests directed at that same website. Now, cookies are one of the most used mechanisms for authenticating and identifying users on the web. And they are also subjected to the same origin policy. So this means that cookies set by domain A are only accessible by domain A. So for example, domain B cannot access the cookies of domain A and vice versa. Now, if we apply these cookies to the example on the left, we'll see that the first request will only contain the cookies of domain A, and the second request only those of domain B. Now, because this last request is a cross-site request, these cookies are called third-party cookies. Okay, so I just want to give an example of how ubiquitous and implicit these cross-site requests are on the actual web. So say we want to visit a certain website, let's say cutekittens.com. And what do we expect to find? Of course, pictures of cute kittens. Now, this is not very realistic because, of course, the owner has to sustain a website, he has to pay for the servers and so on. Maybe he wants to even make a profit. So for this, he includes some advertisements. Okay, so these are fetched from other domains, from the advertiser's domain. Also, he wants to make the website a little bit more functional. So he wants to make it a little bit more user-friendly. But then again, he doesn't want to reinvent the wheel. So he is going to make use of scripts that are available in public JavaScript libraries. And for this also, a cross-site request will be sent. Now, of course, most websites nowadays have social media widgets, so he also wants to include those. And again, cross-site request will be sent to additional domains. So in the end, I think you catch my drift. There are a lot of third parties involved when you just visit a single web page. And when you have a cookie of those third parties, these will be also included in those requests. Okay, so let's start with the most well-known cross-site attack called cross-site request forgery, or CSRF. And in this attack, the attacker actually wants to perform an authenticated state-changing request to the user's account. So he can do this by including a simple script. We'll retake the example of cutekittens.com. So again, the victim will visit this website, but the person behind this website actually has malicious intent. So he wants to target the users of doggobank.com by including this little script, this little line of HTML code. So he tricked the browser into thinking, I'm going to fetch an image, but actually this request will request a money transfer on doggobank.com. Okay, so the browser will gladly send a request because he thinks it's just fetching an image. And of course, the cookie of the user is included, which authenticates the request. So this looks for Doggobank like the user actually did this himself. Okay, so I want to give you some context about this attack. It was included in the OWASP top 10 list. It's a list of the 10 most critical risks in web applications. So in 2010, it was took place on the fifth. It was on the 5th place of this list. Then in 2013, it dropped to the 8th place, and in the last instance, in 2017, it was completely dropped from the list. So this is actually a good sign, because it means that a lot of web developers are aware of this problem and have implemented the additional protection mechanisms to protect their users against these attacks. Now, this doesn't mean that the attack isn't relevant anymore, because so there are a lot of frameworks that integrate defenses automatically, and this makes the attack. This is one of the reasons why it was dropped from the list, because there are a lot more defenses and more easily they can be more easily be implemented by web developers. But this doesn't say that it's not relevant anymore, because last year in August, this article was published. It's about the open EMR system that could have exposed millions of patient records due to a CSRF vulnerability. And also in September, this article was published. And here also a CSRF vulnerability could have been used to attack the PHP-MyAdmin. And then this one in October of last year, TP-Link wireless routers were vulnerable for this attack. Okay, then the next attack is a little bit less well known. It's about cross-site script inclusion. So here the attacker actually does not want to perform a state-changing request. He is actually going to steal some information. So for this he uses the response that is returned upon the request. But of course, the same origin policy doesn't permit the attacker to just read this data. But there's a little bypass for this. Scripts include from different origins can be executed in the same environment. So he actually is going to target dynamic JavaScript files. Those are JavaScript files that are generated based on the user that requests them. So this authenticating cookie authenticates a user, then the JavaScript file is automatically generated and returned. And this often has some sensitive information that the attacker then can steal. Now, for example, here he can include this script. He's going to request a dynamic JavaScript file from doggerbank.com. And then this script will be executed in the same environment as the script of the attacker. So we'll see some examples. So for example, this could be a returned dynamic JavaScript file. You see that the user is named John Doe and has a balance of 1,500 euros. So the attacker actually wants to gain this information, but he just can't read the script file. So he's going to execute an additional script file that he has written himself. And simply, he's going to send the contents of this variable to his own servers. And there he can read this information. Now, another example is this one. So here the website DockerBank wants to make a string of some secret data. And the attacker can then gain access to this by just overriding this function. So again, it's executed in the same environment. When this function is called, actually, this is going to be the function that is executed. And again, the data will be sent to the attacker's servers. So this attack is described in the paper of Lekis et al. And I think there's a lot of other examples, so it's definitely an interesting read. Okay, the next attack is about cross-site timing attacks. Here again, the attacker wants to steal some information. For example, he might want to know if the user has an account on a certain website or not. This can then be facilitated, for example, for targeted phishing. So what do you get to see when you visit twitter.com? With a fresh browser, you don't have any cookies. You get to see a generic login page. Now, in the other case, when you have an account, you're authenticated by a cookie. You get to see a news feed or a Twitter feed, advertisements, maybe some messages. And this is the difference that the attacker wants to abuse to get to know whether a user has an account on a certain website or not. So again, he just can't include these links into an iframe and then just read this. Again, he has to find some bypass to get this information. And he can do that by using a side channel. For example, the difference between the login page and the actual Twitter feed, there's a difference in size, in resource size. And that's the thing he's going to abuse. So here we see that he refers to the index page of doggerbank.com, but he uses an image tag. So the browser will eventually throw an error. But that's actually that's something that the attacker is going to use to do a timing of the downloading of the resource. So he starts a timer when the request is sent, and then when the error is thrown, he's going to stop the timer. And this difference in timing depends actually on the difference of the resource size. So this attack was described in the paper of Borch et al. And here they showed that it was possible to find out if somebody has an account on a certain website or not, and even how many items were in an online shopping basket on a shopping website. Now, of course, there are some caveats here because of network latency and instability. Because, of course, the timing is influenced by additional network instabilities that act as noise. But there's been a solution for this. These are called browser-based timing attacks. And here, actually, the timing starts from the moment that the resource is completely downloaded. Then it's going to be parsed. So the suspend event is going to be thrown when the complete resource has been downloaded. And the error will be thrown when the parsing fails. And again, this timing actually depends on the size of the resource. But here, the noise of network latency and such are not calculated in the timing. Also, if you want to read more of this, Van Gutem et al. Published a paper about this. And Tom Van Gutem is also the co-author of the paper I'm explaining today. Okay, then that's enough about the cross-site attacks. Let's talk about tracking, which is actually the exploitation of implicit identification of users. So in this case, a victim or a user wants to read some news on catnews.com. Okay, the browser is going to fetch the web page. But on this web page, again, a social media widget is included using this script. So of course, the browser again will send a cross-site request. Now, if the user has any cookies of parbook.com, this social media website that of which the script is included on catnews.com, this cookie will be included. So parbook.com actually knows that this user visited catnews.com and any additional information like the page that he read. But also note that if you don't have a cookie of parbook.com, parbook.com has the ability to set new cookies using the response. So he can assign a unique ID to the person that read this article and then start building information with this ID, because this cookie will be saved in the browser, and every time the browser notices this script reference, the cookie will be sent to parbook.com. Okay, so this is the general ID. The more domains that contain the script, the more information Parbook will get. So then a unique browsing profile can be aggregated of the user, and then this data can be used for data auctioning or targeted advertisements. Okay, so I also want to make clear how ubiquitous this tracking problem is. So in the paper Tracking the Trackers of Yu et al., they have done a study of 200,000 German users in about a week, I think. And here they found that 95% of the visited pages contain third-party requests to potential trackers, and of those, 78% attempted to transfer unsafe data. So it's rather ubiquitous also. Okay, then of course users can protect themselves by using privacy-oriented browsers or installing extensions. But because these companies that perform tracking are actual legal entities, they have to adhere to certain laws and regulations. So a solution might be the juridical perspective. Now, I think we all heard of GDPR. It's been highly anticipated. And Clicks and Ghostry did a joint study of the actual differences after the implementation of GDPR. So they found, for example, that the average number of trackers per website actually decreased. So I think that's quite a good result. Also, most advertisers lost reach. They are included on less domains, which is also kind of nice. But then Google slightly gained reach. And this means that the information becomes more aggregated in one company, which is actually not the intention of GDPR, I think. So also in the study, they again say users still have the responsibility alongside of GDPR to be aware of this privacy issue and use these privacy enhancing extensions. Okay, so then we've come to the third-party cookie policies. Let's see which ones are available to us. For example, we have some built-in browser options. The first one is, I think, the most widely available one. It's just the option to block all third-party cookies. So this is quite effective, and I think also rather simple to implement. But on the other hand, it's quite intrusive, because a lot of benign web functionality actually relies on those third-party cookies. So maybe an answer might be the more targeted and advanced mechanisms, like Firefox tracking protection, Opera ad blocker. These make use of blacklists and only block cookies and requests that are directed at blacklisted domains. But, in the next slide, I will explain some more about these blacklists. And then we have also Safari Intelligent Tracking Prevention, which uses more of a machine learning approach. And also, of course, users can install extensions like ad blockers and privacy protection extensions to enhance their privacy. Okay, so these are all client-side mechanisms. They perform on the computer of the client. But I also want to be clear, so there are server-side solutions to cross-site attacks, but here in this paper we focus on those client-side mechanisms. So how do these more advanced mechanisms actually work? Well, they have to decide whether to block a request or cookie, and this can be based on certain criteria. Example is blacklists. A well-known organization that hosts some of these blacklists is called EasyLists, and here you can see such a blacklist. It's actually just a list of expressions, and when a domain matches with such an expression, the policy can decide to block this request or to strip the cookies. Now, these lists are publicly available and systematically updated, so the policies can just fetch the list online and then use it. Now, there's also a machine learning approach in protecting the privacy of users. An example is Safari, which uses this. So here, actually, the browsing behavior is used to construct a personal on-device blacklist. So if you interact with a domain a lot on a first-party basis, then of course that's not going to be blacklisted, although it can be a tracker. So this is a little bit more advanced. Okay, so I also want to talk about same-site cookies. We also tested this in our evaluation. So this is actually an in-depth defense against these cross-site attacks. And you can think of a same-site cookie as a generic cookie with an extra attribute. And like most cookie attributes, it's decided by the website that sets the cookie and enforced by the browser. And the website can assign one of two values to the same attribute, same-site attribute. The first one is strict, and this means that this cookie can never be included in any cross-site request. And the other value is lex, and here it's more or less the same, but there are some exceptions to it. For example, it can still be included in cross-site requests that are also top-level GET requests. This means that the address bar in a browser changes upon navigation, and also it can be included in cross-site requests that are initiated by pre-render functionality. Okay, so adoption by website is rather slow. I think Chrome implemented the same-site cookie in 2016 as the first browser, but still not a lot of websites use this actually. The only website or popular website that I know that does so is Dropbox, and they even have written a blog about it, so that's also very interesting to read if you're interested in that. Okay, so let's see how we can use same-site cookies to protect our users against cross-site attacks. So again, Cute Kittens and Doggo Bank. So this time, when a user logs in for the first time on doggobank.com, the authenticating cookies will be set using same-site cookies. And as we can see, they've chosen for the strict option, so these cookies can never be included in any cross-site request. Also note they can still set generic cookies, like here, for less security sensitive purposes like language settings, for example. Okay, so the attack is performed again, and we'll see that only the generic cookies will be included in the cross-site request. So this means that the request isn't authenticated anymore, and DocoBank will not go through with the money transfer. Okay, so why do we actually want to evaluate these third-party cookie policies? Well, the first and main reason is that browsers exhibit inconsistent behavior. This can be due to interfering web standards, but also due to unintended side effects from code modifications, which is not detected upon release of a new browser version. Also, there's a very saturated market of ad blocking and privacy extensions, and none of those extensions actually have a clear quantification of quality, because most user reviews are actually based on usability instead of effectiveness. So what we want to do is perform a automated evaluation of effectiveness such that we can better compare the extensions to one another. Okay, so let's talk about the comprehensive evaluation that we did. For this, we developed a framework, and we kind of went with a black box approach. And the first reason is because browsers consist of millions of lines of code, and source code isn't even always available. Also, there's many extensions that we want to test, so according to us in these both cases, code review would not be that feasible. So this is how we implemented the black box approach. We started with a browser instance, which is the actual black box. And this is the combination of a browser, an extension, and a configuration. For example, you can take Firefox, enable Firefox tracking protection, which is a browser instance, or Chrome and install AdBlock. Then this browser instance is given to the framework, which will run all kinds of tests and eventually output bypass detection data. Okay, so this is the general design of the framework. Here is the browser instance, and the blue part is the actual framework. So we instruct the browser to visit some web pages that we host ourselves. But I'll zoom into the more important parts. Okay, so we control the browser in two ways. The first and most convenient way is through Selenium. It's a browser automation tool. We install extensions, we start the browser, we instruct it to visit some web pages. But unfortunately, not all instances are supported by Selenium. So for these cases, we have to fall back to the command line interface, which isn't that convenient, but still gets the job done. So we also host a little web server. Here we host some pages that initiate cross-site requests to blacklisted domains. And the proxy in between the browser instance and the web server actually makes us able to detect which web mechanisms initiated which requests, and which of those, in turn, could bypass the active policy in the browser. Okay, so of course, to make our evaluation comprehensive, we had to have a comprehensive list of these web mechanisms that are able to initiate these cross-site requests. And when we started, there did not exist such a comprehensive list, so we had to do this ourselves. Of course, we had access to a lot of valuable sources, but in the end, we came to 7 different mechanism groups. For example, this group, it's the Appcache API. It's used to cache web pages. So for example, when internet connection is lost, still the browser can provide those web pages to the user. So in turn, to cache something, you first have to fetch it. So for fetching, actually a cross-site request can be sent. So this is how we use this web mechanism. Also, of course, HTML tags can initiate these requests, like we already saw, script tags or image tags. Then also some headers. Link headers are often used to fetch resources in advance to improve loading times. And then you can also be redirected to a cross-site domain. Although most of these third-party cookie policies actually do not consider this as a cross-site request, because eventually the user will interact in a first-party context with the previously cross-site domain. Okay, JavaScript also has some APIs to initiate these requests. And this mechanism group is actually very interesting. It's about JavaScript embedded in PDF files. So some PDF readers actually allow you to execute JavaScript and some even allow you to initiate cross-site requests. An example is PDFium, the PDF reader of Chromium-based browsers. And this method, for example, can send form data to any specified domain. And then lastly, we have the service worker API, which is more or less the same as the JavaScript group, but executed in a service worker instance. Okay, so here's an overview of all the browsers and extensions that we tested. So we tested 7 different browsers, of which 5 support same-site cookies, and then 31 ad blocking extensions and 15 tracking protection extensions. Okay, so this is the data for the browsers. It's a lot of data, but I'll highlight the most important parts. So here you can see the 7 different browsers and their built-in options. On the top axis, you can see the 7 different mechanism groups. In this table, a full circle means that the mechanism, or at least one mechanism in the mechanism group, was able to initiate a cross-site request to a blacklisted domain, including cookies. A half circle means that this request did not contain any cookies, and an empty circle means that no request was sent at all, so it could be blocked by the active policy. Okay, so let's highlight some important things. So as I said before, the PDF reader inside Chromium-based browsers allows us to send cross-site requests. But what's even more interesting is that if we enable the option to block third-party cookies, still third-party cookies are included in these requests. So it actually bypasses this option. Then the other options to block these cookies in Safari 10 and Edge 40, we can see they are not really effective because multiple mechanisms can actually bypass this option. And even in Edge, we did not detect any difference from when this option was enabled or not. Then for the more advanced mechanisms, in Opera AdBlocker and Firefox tracking protection, for example, we see that they are also not as effective as advertised. But on the other hand, Safari 11, in which Safari Intelligent Tracking Prevention is enabled by default, it's actually quite effective because if we don't count the redirects, it actually managed to block all third-party cookies. So that's quite good. Okay, so this is the table for the ad blocking extensions. I won't show you the table of privacy extensions because we can draw the same conclusions out of it. So here we actually grouped these extensions together in sets because otherwise the data wouldn't fit in the table. And we grouped them together if they had the same outcome mechanism group-wise. So for example, if we take set A1, the set contains 3 extensions. And all of the extensions in this set were bypassable by at least one mechanism of each mechanism group. Okay, so again, the most important part. I will also explain how we managed to bypass this because it illustrates how, despite web standards, browsers still differ a lot from each other. Okay, so this is the Appcache row, and we can see that almost all extensions can be bypassed using the Appcache API. This is how we did it. So on the same domain, we refer to the Appcache manifest file. And in this manifest file, we refer to the cross-site domain. So this is actually, this initiates a request to the cross-site domain to fetch and eventually cache the web page. Now, the reason why a lot of extensions could not block this request is because the tab ID of the initiated request is actually -1. And this means that no browser tab is associated with this request. Now, this is generally the case with requests initiated by browser background processes. And as an extension developer, you do not want to touch these because if you block such a request, you can break browser functionality. And this in turn can incline browser users to deinstall your extension. Okay, the next one is the row of the column of the service workers. And here we can see that almost all extensions in Chrome and Opera could be bypassed. But this is not the case for Firefox extensions. And we also found a reason for this. So For the service workers, we use these APIs. And again, similar to the previous problem, here also the requests have a tab ID of -1. So this means they are not associated to a browser tab. But in Firefox, that's not the case. They have an actual positive tab ID. So here in this case, the extension developers know in Firefox, okay, this is certainly not a request initiated by the browser itself. And in Chrome, they have to apply other means to actually get this information. So this illustrates why it's important to be consistent in this information and how it actually can be applied to be more effective in blocking these requests. Okay, so here it's kind of the opposite. So now almost all browsers in Chrome and Opera managed to block the request, but all extensions in Firefox actually were bypassable. And there's actually one mechanism that caused this. Is the mechanism for fetching the favicon. So the favicon is the little icon that you sometimes get to see next to the title of the page in the browser tab. And using this mechanism, you can refer to any Crosssite domain to fetch this favicon. This is how we've done it. So when we detected it, this problem was already reported, but still, but now it's fixed. So this is not a problem anymore. Okay, then again, the PDFium case. So here, all extensions in Chrome and Opera can be bypassed using JavaScript embedded in PDF files. Now I'll explain this one in a bit more detail. So the PDF reader of Chromium-based browsers like Chrome and Opera, called PDFium, is able to initiate a GET or POST request to any specified domain. And you think that also these requests should be interceptable by the extension API, such that ad blockers and privacy extensions can actually act as a complete third-party cookie policy. Well, this is not the case because PDFium is actually considered a plugin or extension, and by rule in these browsers, extensions cannot intercept requests from each other. So this is more of a security precaution because otherwise malicious extensions could influence the benign extensions. But still, this means that the request initiated by the PDF file is completely bypasses the extension API, which makes every ad blocking extension and privacy extension unable to act as a complete third-party cookie policy in Chrome and Opera. Also, like we saw, it even bypasses their own built-in option to block third-party cookies. Okay, then for the extension, a little recap. So no extensions manage to block all third-party cookies. One of the reasons is the insufficient extension API provided by the browsers. For example, the PDFium case and the favicon case in Firefox, which is now fixed. And also sometimes the API is unclear, like the tab ID that does not give enough information if the request should be blocked or not. And then for these smaller extensions, we also found some common mistakes. For example, that the extension developers did not request sufficient permissions to intercept certain requests. Okay, so we also tested the Samesite cookie policy. In Chrome and Opera, we found that the pre-render functionality can be bypassed. Can be used to bypass the Samesite cookie policy. So this request actually contains the lex and strict Samesite cookie, while it's only allowed to include the lex Samesite cookie. Then in Edge, we found multiple bypasses for both the lex and strict Samesite cookie. And Firefox and Safari, we did not detect any bugs. Okay, so this is a small example of how such a bypass can be used to make an attack effective again. So here, the attacker just has to change this line in its HTML code. So here, instead of using an image, he now uses the pre-render functionality, which will include the strict same-site cookies and again authenticate the cross-site request. Okay, so we also evaluate our own framework. We want to know if we were complete, if we use all mechanisms that can initiate these cross-site requests, and also if the bypasses that we found were actually novel. So for this, we did a distributed crawler setup. We intercepted all headless Chrome network traffic using Linux network namespaces, and we analyzed all the intercepted requests. So this gave us an indication of completeness because we did not encounter any web mechanisms that were used to initiate these cross-site requests. And also, we did not find any abuse of defined bypasses by trackers. So this indicates also that the bypasses that we found were novel. Also, we did this crawl on the Alexa Top 10,000. It's the top 10,000 most popular websites according to Alexa. And on each website, we visited 20 pages, which total to a number of 160,000 pages. Okay, so the initial evaluation was done like half a year ago, I think. So in the meantime, of course, the browsers have updated. So I want also to go over what has changed in the browsers. Are there any significant bug fixes? In Chrome 71, they fixed the issue where the built-in option to block third-party cookies could be bypassed by PDF files. And in Opera 57, they fixed also the pre-vendor bypass for same-site cookies and partially fixed the ad blocker. So now also all requests initiated by HTML mechanics are blocked. So that's all the bug fixes that we found. This shows us that bug fixing is rather slow. It's maybe understandable because browsers, of course, are complex things. Okay, now we've come to the conclusion. So in the initial findings, we found that built-in browser policies can be bypassed. These are same-site cookie policy and the third-party cookie policies, but also the more advanced mechanics, like Opera Adblocker and Firefox tracking protection. Also, we found that all ad blocking extensions and privacy extensions could be bypassed. This can be due to the extension API that is in some cases insufficient or not really clear about things, but also in these smaller extensions due to common mistakes made by the extension developers. So of course, in the future, we want to go further with this framework. We want to expand it policy-wise. We want to include other policies like private browsing mode and CSP. And platform-wise, we also want to include mobile browsers because a lot of users now use their smartphone more than their laptop to surf the web. So our goal is to make a tool for a comprehensive and automatic evaluation of these policies, which can then be used by browser vendors to test their browsers before they release it. So lastly, I want to give you an illustration why we think such a tool is important. I want to illustrate this using the example of the pre-runner bug that can be used to bypass the same-site cookie policy. So it was originally reported for Chrome 57. Of course, we reported this immediately. Then it was still present in versions 58 till 61. And it was fixed, or we didn't detect it anymore, in version 62, 63, 64, and 65. But then, unfortunately, it came back in version 66 till the latest version of 71. So according to this, this really illustrates why it's important to have an automatic and comprehensive evaluation, such that bugs that even are known can be removed from the policy before the browser is actually released. Okay, so this was my presentation. I hope you found it interesting. If you want more details about the evaluation, we have a website. Here you can see all browsers that are tested. We update it when new browsers come out. And also, if you want to follow us on Twitter, these are our Twitter handlers. Okay. So if anybody has any questions.
So if you don't have questions now, maybe maybe later it's a dinner. Final chance now, nobody? So then let's thanks our speaker again.